Much for the invitation. I really appreciate it. It's a pleasure to be here, even remotely. Yeah, so today I'll be telling you about a very old topic, an old school topic about the evaporation of charged black holes. And this is work that I've done together with Adam Brown, Jeff Pennington, and Misha Usatyuk that should appear very, very shortly. Um, the question that motivated us is very simple. Consider a black hole that doesn't have any surrounding matter around it, that has a mass m, a charge q, and an angular momentum j. How does this black hole evolve with time if there's no matter around it? Well, for a generic black hole, it will eventually go into an equilibrium state that has this mass, charge, and angular momentum that's given by the typical Kerr-Newman solution. And afterwards, classically, nothing will happen. Quantum mechanically, however, as you all know, black holes emit Hawking radiation, and Hawking radiation can change the mass, the charge, and the angular momentum through energy conservation, charge conservation, and angular momentum conservation, respectively. So, given these three parameters, how does such a black hole evolve with time in flat space? Um, and this might seem a question that Hawking should have been able to answer in the 1970s, right? Hawking computed the rate of evaporation into neutral particles. Later, a year or two later, Gibbons computed the evaporation rate into charged particles. So putting those two results together, it would seemingly, you would seemingly get an obvious result for this question of how the mass changes with time. However, I have to give you a spoiler and to convince you not to leave the talk. And the spoiler is that when we start with a large enough charge, quantum gravity corrections are actually critical to describe the evaporation history of a black hole. By quantum gravity corrections, I mean that the quantum field theory in curved space-time approximation that leads to the standard, Hawking radiation result actually fails. And it actually fails for the majority of the lifetime of such a black hole, as long as it has as long as this black hole has large enough charge. And we'll be studying two types of particles that, of course, exist in our own universe as well. Neutral particles, such as photons, radiation into neutral particles, such as into photons or gravitons. And for such forms of radiation, it turns out that perturbative quantum gravity effects will actually be very important at late times. And evaporation into charged particles, the one that's responsible for black holes losing their charge. And for the radiation into charged particle, it will turn out that a combination of perturbative and non-perturbative effects will be important to describe the evaporation. And the techniques that we'll use in order to understand evaporation into charged particles actually have to do with techniques that come from string theory, even though in here I'm not actually discussing any type of stringy corrections to Hawking radiation. It's just that we can use string theory techniques to quantitatively understand how charged radiation is emitted in the regimes when quantum gravity corrections become important. And along the way, we will discover many phenomena that are analogous to those seen in atomic physics. So in atomic physics, we oftentimes describe the emission spectra of atoms. And, there's a plethora of phenomena that people discovered in the past century. And we'll discover analogs for the phenomena that we see in atoms in the case of black holes. Any questions? Okay, so if there's no questions, let me start with the simplest thing that happens when a black hole has mass charge and angular momentum and it evaporates. Namely, the first thing that happens is that a black hole will emit a lot of neutral particles. if its charge is large enough, it will emit a lot of neutral particles, such as photons and gravitons in our own universe. And the evaporation into photons and gravitons is such that the black hole actually loses most of its classical angular momentum. So if you do it, you could do a back of the envelope calculation even to see that there is a preferred emission channel into uh, uh, photons and gravitons whose components of the angular momentum point in the same direction as the component of the angular momentum of the black hole. And because of angular momentum conservation, the black hole will start losing its spin. And it will lose its spin a lot more quickly than losing its charge. Now, step two is that once it loses all its spin, it will end up somewhere in this plane of mass and charge. Here I drew the extremality line. So a black hole can only exist if its mass is bigger than its charge, if it has zero angular momentum. And at this point, our goal is to understand what happens. Which way does it evolve from here? Um, so we should analyze the competition between two types of particles being emitted. The ones that make the black hole lose its energy, and the one that make the black hole lose its energy and charge, namely charged particles. So let's do a back of the envelope calculation to see which one is more important. So for neutral particles, when they're massless, they get emitted with a thermal spectrum, meaning that even when accounting for things like gray body factors and factors that tell you how a neutral particle, what happens to a neutral particle once it escapes from the near horizon region of a black hole. Even when accounting for that, you'll find that the energy flux into such particles is always a polynomial in the temperature, following Hawking's calculation. And a polynomial in the temperature for a charged black hole can be, when it's maybe close enough to extremality, can be expressed as a difference between its mass and its charge to some power. So the idea is that the flux here is a polynomial in the difference between mass and charge. For a charged particle, the mechanism of emission is actually very different. So first of all, when the mass of a charged particle is smaller than its charge in Planck units, this drives a black hole away from extremality, right? At least naively. That's because the new extremality bound is big Q minus little q, and the new mass of the black hole, at least naively, we'll see actually that that computation is wrong, is big M minus little m. So if you compute the difference between the new mass and the new charge, you'll find that it actually moves away from extremality. Now, another difference from neutral particles is that charged particles don't get emitted with a thermal spectrum. That's because they get emitted through Schwinger pair production. So in the near horizon region of a charged black hole, there's actually a pretty strong electric field. And that electric field creates pairs of positrons and electrons, sometimes with one particle behind the horizon and the other outside the horizon, sometimes with both particles outside of the horizon. In either case, there is a particle that's accelerated, a particle that has the same charge as the black hole. Let's say the black hole is positively charged and that particle is a positron, gets hugely accelerated and escapes all the way to infinity. So that's how a black hole goes away from extremality. However, Schwinger pair production is a non-perturbative process in quantum field theory. In the sense that there is an instanton calculation that shows you that this process is non-perturbatively suppressed. So let's use Schwinger's result. This is the thing in the first equality to estimate what Schwinger pair production would be for a charged black hole. So
Can I
little
can
m
I can
is
I actually ask you a
yeah,
question here? The the
yes,
the,
yes,
the
please.
formula you quoted for the Schwinger pair production, this is in flat space time. This
Yes,
is
yes, yes,
not
yes. So
near.
this
This would not be
is the
valid near
most.
the horizon.
Yep, yep, yep. So this is the
Yeah.
back of the envelope calculation.
Okay. All right.
So it's a back of the envelope calculation in which we're just taking Schwinger's flat space formula and plugging the electric field wherever it's strongest in the space-time. And it's strongest out right outside the horizon. So to get kind of a sense of the order of magnitude for this decay rate, to a good approximation, we could just take the electric field outside of the horizon and see what the decay rate is from there. And it's actually quite a good approximation, it turns out. The reason why is because the instanton, the size of the instanton that gets created in the process of pair production is actually much smaller than any other scale of curvature in the problem. So it's much smaller than the horizon size or the in the case of near extremal black holes, it's much smaller than the size of the ADS2 near the size of the ADS2 curvature in the near horizon region. So to a good approximation, that instanton lives in flat space. But what I want to emphasize here is that if you plug in the electric field for one of these black holes, actually the bigger the black hole is, the smaller its electric field by the horizon is. You get a formula that is exponentially suppressed in big Q. Now, it's exponentially suppressed by a factor that turns out to be very, very, very tiny, because that factor contains the ratio between the mass of a charged particle and the charge of a charged particle, which in Planck units for the positron is actually a very, very tiny number. So Q has to be enormously large for this to be exponentially suppressed. It has to be bigger than this value, Q star. This value, Q star, turns out to be 10 to the 44 coulombs in our own universe. And the corresponding value that a black hole at extremality would have would be 10 to the 6 solar masses. So the idea is that if we start out with a black hole in this region, to the right of the vertical blue line, we will be driven towards extremality by neutral particles. And the pair production into charged particles will be exponentially rare. So essentially, because of that, we will go exponentially close to extremality. How close to extremality? Well, this calculation, which is just a QFT in curved space-time calculation, suggests that we will go exponentially close to extremality with precisely the factor that's given by the exponent in the Schwinger pair production rate. Um, what happens once we reach this region very close to extremality? Well, we actually know that once we reach the region close to extremality, the calculation, the back of the envelope calculation that I presented, suffers for problems for both neutral and charge radiation. So let me mention what this problem is. So for a neutral particle, it has long been known that close to extremality, there's something funny happening with the thermodynamics of the black hole. Namely, there seems to be a breakdown of the thermodynamics. Let me explain what that actually means. This was described in the paper by Preskill and collaborators in the 90s. Well, according to the QFT in curved space-time approximation, the average energy of a Hawking photon is proportional to its temperature. However, if you look at the energy that a black hole has above extremality as a function of its temperature, this curve for the energy above extremality goes like temperature squared times a scale that we'll call the energy breakdown scale. For a black hole in flat space, for a charged black hole in flat space, this energy breakdown scale is like m Planck divided by the charge cube of the black hole. So the problem with this plot is that if I have a black hole that's anywhere below has an energy anywhere below this intersection point between the average energy of a single Hawking quantum and the energy of a black hole above extremality, the black hole wouldn't actually have sufficient energy to lose to actually remain above extremality. So the QFT in curved spacetime approximation would tell you that naively you'd radiate a photon that would take a black hole below extremality, making it super extremal and ending up with a naked singularity. Now, of course, this sounds crazy, um, but there has to be a resolution to this, right? And the resolution is that once a black hole reaches such small temperatures, it turns out that quantum gravity effects become important. And this is something that we've discovered in recent years. It's that if you do an expansion of the metric, you study quantum fluctuations of the metric in near extremal black hole background. If you're strictly at extremality, people had discovered that there's a set of zero modes for the metric that exist on this background. So if you take the Einstein-Hilbert action and plug in your classical extremal background and add small fluctuations, you'll find a set of flat directions. This set of flat directions, roughly speaking, correspond to, just to give you some intuition, to a set of large diffeomorphisms that act on the near horizon region that change the way in which the near horizon region is glued to the asymptotic part of the space-time. So in the case of extremal black holes, the near horizon region looks like ADS2 cross S2. And there is a set of large diffeomorphisms that act in the near horizon region that from the perspective of the entire space-time, they're actual physical perturbations of the metric that change the geometry of the space-time, but don't change the Einstein-Hilbert action. So in principle, if we really want to study such black holes quantum mechanically, but at very low temperatures, we have to integrate over this set of zero modes of the metric. Now, integrating over a set of zero modes is very tricky because most of the times you'll get divergence associated to an integral over zero modes that live in a non-compact space. However, we're not actually interested in the purely extremal limit, right? We haven't ended up with a black hole at exactly zero temperature. In the plots that I've shown previously, we showed that there's a dynamical process that drives the black hole towards very small temperatures. So let's analyze what happens to these quantum fluctuations once we look at small temperatures. Well, for that, we have to change the background. We no longer have to study fluctuations around the extremal background. Rather, we have to study fluctuations about the background metric of a near extremal black hole. So namely, we have to deform the extremal metric by some temperature-dependent term, classically, and then expand into fluctuations. And the interesting thing that happens is that once you look at the modes that were zero modes exactly at extremality, these modes gain a non-zero weight once the temperature is slightly non-zero. And this weight, oh, sorry, there's a typo here. T should be in the numerator rather than the denominator. And the weight of these modes is proportional to the temperature of the black hole. So for very small temperatures, these modes have extremely large quantum fluctuations. But luckily, they are captured by a theory that gives us full control over what is happening, namely by the Schwarzian theory, which turns out to be a one-loop exact theory. So it turns out that all other modes of the metric are gapped. They're in the quadratic expansion. Their mass is temperature independent. It only depends on the charge of the black hole, except for this set of modes whose mass is proportional to the temperature. Now, the set of modes that are gapped, that have a mass proportional to the charge of the black hole, to the size of the horizon, end up giving you a set of logarithmic corrections to the extremal black hole entropy. And this set of logarithmic corrections was studied by Sen and collaborators at the beginning of the 2000s. The set of modes that are very light actually give you a much more drastic effect, a much more drastic quantum correction close to extremality. And this is something that Sen and collaborators missed when they were looking in the strictly extremal limit. Namely, the set of modes give you a one-loop determinant that is proportional to the temperature of the black hole. So let's compare it to the quantum corrections that go like log S naught. As the temperature goes to zero, log of the area just goes to a constant. While on the other hand, as the temperature goes to zero, this one loop determinant makes the entire partition function vanish. So let's, instead of looking at the partition function, let's look at the density of states of such black holes. So here on the left, we have plotted the density of states with the red curve representing the semi-classical answer that ignores the presence of these modes that have large quantum fluctuations. You see that the density of states at large energies above extremality is exponentially large, and as you approach extremality, it goes to a constant. On the other hand, the quantum-corrected density of states agrees with the semi-classical prediction at large energies above extremality. But when we go below this scale, the breakdown scale at which Preskill and collaborators predicted that the thermodynamics would break down, we see that quantum corrections become important and the density of states entirely changes, to the point where exactly at the extremality, we find that the density of states goes to zero. Okay. This thermodynamic correction also changes the way in which the energy that a black hole has above extremality. Instead of making it quadratic in temperature, the one loop determinant that I presented earlier actually makes the energy above extremality go linear in temperature with a coefficient that goes like 3/2. So naively, now you might say, oh, well, since the black hole has an energy above extremality that could be bigger than the energy of a Hawking photon, the thermodynamic breakdown puzzle should be resolved. However, this is a small cartoon because we haven't actually done the calculation for what the new energy of the Hawking radiation is at such low temperatures when accounting for quantum corrections. Yes.
Can I ask a question?
Yeah.
In the partition function, which you showed earlier,
Mm-hmm.
there was also a log t term of some sort. So
Yes.
you have a t in the exponent, and if I exponentiate that t to the 3/2 down there, I would also get a
Uh-huh.
log term.
Exactly.
This does not affect your energy relation?
Yes, it does. It does. It does. Exactly. That's where the free half t comes from.
Ah, that's the one. I see.
That's
Okay.
the one, yeah. So this is
Okay.
the semi-class. The thing in the exponent is the semi-classical gives the semi-classical entropy of the or semi-classical free energy of the black hole. It actually gives the fact that the free energy goes like the temperature implies that the energy above extremality goes like the temperature squared.
Oh yeah. Yeah. Thanks.
Um, and the logarithm is the thing that corrects the energy above extremality at very small temperatures. So this is exactly where the free half t comes from. It's the one loop effect. And you could see in this plot that the one loop effect is actually the dominant one at very low temperatures. Um, any other questions? So to fully address this thermodynamic breakdown puzzle, we need to answer what happens to the radiation. So, and to fully describe the history, and that's also required in order to fully describe the history of the black hole. So we will answer the following questions. How close to extremality do we truly get? how is the spectrum of neutral radiation affected? And how is the rate of charged particle pair production affected? And from all this, we will derive the full evaporation history of a black hole. And the evaporation history of a black hole will turn out to be quite crazy, as I will probably convince you in the next 30 minutes. Okay, so first let's discuss the evaporation into neutral particles. So to account for evaporation into neutral particles, we need to understand how the evaporation rate, or how the particles that are emitted from the near horizon region are affected by the fact that the near horizon region has a metric that's strongly fluctuating. And for convenience, we will consider a massless scalar field as an example. So we'll consider Hawking radiation into a massless scalar field, though we've done the calculations for photons and gravitons. So even though we don't have a massless scalar field in our own universe, it's convenient to consider it for simplicity. We can consider to compute the evaporation rate, we can essentially try to understand the process of stimulated emission for a black hole. And from that, we could get a spontaneous emission rate. We can consider an incoming wave that comes from infinity, and a spherical incoming wave that comes from infinity and goes towards the black hole that has a given amplitude, Bn. And by the time it reaches this near horizon region, the effect that it will have is that it will modify the weight that the modes in the near horizon region will have. And the way in which it will modify it is that to the Schwarzschild action, that is the effective theory for the fluctuations of these near zero modes, one couples an operator that is sourced by this wave at this location, at a region where we separate the near horizon region from asymptotic infinity. To understand how the action is affected, we would first have to compute what the profile of this wave is on this blue line. We know what it is at infinity. We just have to find how we're sourcing an operator that couples to the effective theory that controls the fluctuations of the modes of the metric. And you could solve this classically, and you'll get the answer that I've written here, where Z boundary parameterizes the location where we cut off where we arbitrarily cut off the near horizon region from asymptotic infinity. And we find that even though we turned on a wave with arbitrary amplitude at infinity, at the blue line, at the location of the blue line, if we consider a wave that has small enough frequency, namely frequency that's proportional to the temperature of the black hole, the amplitude of the wave at the location of the blue line will actually be very, very tiny. And this is because this wave has to pass through a potential barrier by the time it reaches the edge of the near horizon region, and that potential barrier can be quite large in the case of near extremal black holes. How large? Well, given that we're interested in frequencies that are, of the same order as the breakdown scale, or as the temperature of the black hole, the product between the size of the horizon and this energy scale turns out to be very small. It's polynomially suppressed in Q. So R plus omega goes like 1 over Q squared, and R plus E breakdown also goes like 1 over Q squared. So essentially, I'm studying to understand how these metric fluctuations affect the rate of Hawking radiation. I am just perturbing the effective theory of these metric fluctuations by a very tiny parameter, by a very tiny coupling to an operator. And We can actually compute there. We can therefore compute the evaporation rate or the transition rate between different states of a black hole using Fermi's golden rule and using first order and perturbation theory analysis. Namely, the perturbative parameter is R plus times E breakdown to the correct power. So the perturbative parameter comes from the gray body factor that the incoming wave experiences, the incoming or outgoing wave experience in between the near horizon region and asymptotic infinity. So applying applying Fermi's golden rule, we simply had to apply Fermi's golden rule. We simply have to understand what the matrix element of the operator O that corresponds to turning on this scalar wave. What the matrix elements of the operator O is in between two arbitrary black hole states, one that has an initial energy EI and one that has a final energy EF. And it turns out that such matter correlators in the Schwarzian theory were actually computed in the past and are just given by this product of gamma functions. So here, gamma plus minus is actually a product of four gamma functions with all possible signs. And the emission rate is suppressed by the small parameter that comes from the gray body factor. So in the case of a massless scalar, the majority of the radiation comes from the S-wave sector, the waves in the S-wave sector. And we can rewrite the product of gamma functions to obtain the overall flux in terms of the sinches and Cauchys. Now, the reason why this formula is actually quite illuminating is that we can easily see that when we take the initial energy of the black hole to be much bigger than the breakdown scale, this formula actually recovers the QFT on fixed background result. Namely, it tells you that the flux is an integral over this thermal distribution that's weighed by the proper gray body factor associated to the probability that the Hawking radiation makes it out all the way to infinity. However, the interesting thing happens when EI is very small, right? When EI and omega are the same order as this breakdown scale. In that regime, we cannot approximate the Sinches and Cauchys by exponentials, and presumably we should see a very big difference from the QFT on fixed background calculation. And indeed we do. So if you look at the spectrum of Hawking radiation when the initial energy is 100 times E breakdown, you see that the quantum corrected spectrum is actually very close to the semi-classical result. So these two lines are very close. But in the quantum regime, where EI is 0.1 E breakdown, for example, you see that the semi-classical result completely differs from the quantum corrected result. Furthermore, an important feature of the quantum corrected result is that the spectrum is actually bounded. This formula that you get from analyzing the exact correlators in the Schwarzian theory actually has the feature that the spectrum is bounded at a maximum energy EI. So this actually resolves the thermodynamic breakdown puzzle that Preskill and collaborators faced. Not only did we find that there are strong quantum corrections to the spectrum of neutral radiation, we also found that there is actually no allowed Hawking quanta whose energy omega is bigger than the energy that the black hole had above extremality initially. So if, therefore a black hole cannot radiate anything that would make it super extremo. So for massless scalars, we can thus look at the fluxes in these two different regimes when the energy above extremality is much bigger than the breakdown scale. You get that the flux is goes quadratically with the initial energy above extremality. But when the energy above extremality is much smaller than the breakdown scale, the power law changes. And it changes quite drastically. So the flux hugely decreases as we approach extremality. The evaporation rate just slows down. How about the evaporation rate for photons and gravitons, since our universe does not have a known massless scalar, as far as we know? Well, one additional subtlety for photons and gravitons is that we cannot ignore the contribution of angular momentum. And this is because angular momentum leads to additional selection rules. So, for instance, if we start with a black hole that has some spin J, and we emit a photon, we can only get to states that have J equals 0. Sorry, this arrow should have pointed to J equals 0. Stay at the same value of J, or increase J by 1. However, the extremality bounds for different spins are also different. It turns out that the metric fluctuations that we studied in the beginning also allows you to see to get a very fine-grained estimate for what the extremality bound is in sectors with different J. And here I'm actually talking about the quantized value of J, 0, 1, 2, so on and so forth. And it turns out that the extremality bound for a black hole that has spin J, as long as the classical value of J is very small, goes like J times J plus 1 times E breakdown. This is the value above the extremality bound that the J equals 0 black hole has. So for instance, if the J equals 0 black hole has a density of states that vanishes when E is equal to Q, the J equals 1 black hole will have a value that vanishes when J is equal to, will have, when the energy is equal to Q plus E breakdown. Now, imagine that we are somewhere here, right? Where the density of states for states that have higher angular momentum, you can see from this plot, is actually quite low, much lower than the density of states for black holes that have lower angular momentum. Then transitioning to a sector with higher angular momentum will become highly unlikely. And this happens even though in the semi-classical computation, the evaporation rate into these three different channels, J equals J minus 1, J, and J plus 1, is about equal. And we can look at this as an example of what happens when the angular momentum of the black hole is 10. So we have a huge black hole, right? But it only has 10 units of angular momentum. When the energy above extremality is extremely large, 10 to the 5 E breakdown, we see that the quantum result and the semi-classical result are about equal. So again, we see that the QFT in curved space-time approximation is correct. However, when we start lowering the energy of the black hole above extremality, we suddenly start seeing that the black hole emits much fewer photons in a direction that would increase its angular momentum. So J prime will be the final angular momentum, and the evaporation rate into photons that take it into J prime equals 11 is much smaller than those that would take it to J prime equals 9. And for instance, when I set the initial energy to be 100 times E breakdown, the evaporation rates into J prime equal 10 and 11 is completely negligible, and I only care about the quantum corrected rate that takes my black hole into a sector with angular momentum 9. So this is all to say that there's a preference. There's a preference for the black hole to go towards even lower angular momentum. Even when we quantize angular momentum, it goes towards J equals 0. And as it goes towards J equals 0, quantum effects become more and more important. And something even more extreme happens at even lower temperatures. So eventually, the black hole will end up with an energy that is here, lower than the extremality bound for a black hole that has J equals 1, but above the extremality bound that a black hole has for J equals 0. Now, in this regime, let's imagine that we're trying to emit a single photon. Well, the problem with emitting a single photon is that a photon will be would force the black hole to change its angular momentum from 0 to 1, right? Because a photon has angular momentum 1, and the only allowed channel changes the angular momentum of a black hole. However, it would also force a black hole to lose some energy. But there's no actual state that has J equals 1 and has a lower energy than where the red triangle is. So this actually forbids the black hole to emit single photons or single gravitons. So what happens at this point? Well, what happens is that the black hole can emit a photon, go slightly off shell, and then emit another photon such that the pair of two photons that are emitted together are actually in a singlet state. That in a singlet state of angular momentum that leave the black hole with zero angular momentum after their emission. And this is a situation that's completely analogous to one that we see in the hydrogen atom. So people study the 2s to 1s transition in the hydrogen atom. And to go from the 2s level to the 1s level, it's actually also impossible to emit a photon for the same reasons. Emitting a photon would increase the angular momentum of the black hole, but there's no state that has angular momentum that is lower than 2s. The type of process that people study for the hydrogen atom is very similar to the type of process that we will study now for black holes. And namely, the difference now in our calculation is that instead of applying Fermi's golden rule to first order imperturbation theory, we have to go to next order imperturbation theory to actually see an allowed decay channel. So we'll get a much more suppressed emission rate than the one that we would get for a single photon, because we're going to second order imperturbation theory in the gray body factor. So the dominant channel consists of emitting pairs of entangled photons in a singlet state. And the flux in such a channel no longer depends on the 2-point function or on the matrix element squared in the Schwarzian theory. Rather, it depends on a product of four matrix elements. So it depends on 4-point functions in this theory. And these 4-point functions can be either time ordered or out of time ordered. In either case, if you sum up all the contributions, you'll get the following decay rate, where you now see that the power that appears in the flux in terms of the initial energy of the black hole is actually much tinier than what we've seen before for single photons. So this process is actually highly suppressed, and if you compute, we can also compute the numerical coefficient in front of this process. So just to give you a sense of the result, if the evaporation rate for the time for a black hole to reach extremality with single photon emissions turns out to be 10 to 800, about 10 to the 800 years. This process going from single photon to diphoton emission suppresses the process even further by another factor of 10 to the 800 because it's the next order in perturbation theory. Anyway, that's that just to say that this makes the evaporation really crazy slow. And similar computations can be done for graviton and digraviton emission. So just to summarize, for neutral particles, Above the line, I'll put the result when the energy, the semi-classical result or the QFT in curved spacetime result, when the energy is much above V breakdown. And below, I'll put what happens when the energy is well below V breakdown and the angular momentum of the black hole ends up being zero. So for photons, the evaporation rate, even semi-classically, is slower than for a massless scalar, but quantum mechanically, it becomes way slower. For gravitons, when EI is much bigger than E breakdown, surprisingly, for Reinstein-Nordström black hole, this is something that people appreciated in the past as well, that surprisingly, the evaporation rate into gravitons is actually of the same scale as the evaporation rate into photons for Reinstein-Nordström black holes in our own universe. Quantum mechanically, it turns out not to be true. The evaporation rate into gravitons ends up being much slower than the evaporation rate into photons at energy scales that are much smaller than E breakdown. So in the initial plot, the neutral particles that would come out of the black hole would be photons and gravitons with almost equal fluxes. And eventually, when the black hole cools down enough, it will only emit entangled pairs of photons and very, very, very rarely entangled pairs of gravitons.
May I ask a question here?
Yeah.
There seems to be a factor four difference between the emission rate for gravitons and photons when
Uh-huh. Oh,
why is that? Why is it a factor of
so
four?
so it's so the fact that even the powers are the same is very non-trivial. The
Yes.
coefficient being the same is
Yeah.
would really be a coincidence. So maybe I can explain slightly why the rates are actually the same. It's because there's when you analyze the emission into gravitons and photons in the Reinstein-Nordström background, you have to be careful to actually properly diagonalize the fluctuation into photons and gravitons. And because the metric couples to electromagnetism in the case of a charged black hole, it turns out that individual fluctuations of photons and gravitons are not actually the diagonal terms. So there's what's called a mixture between gravitons and photons that are being emitted. Now, this mixture changes the wave equation for gravitons and for photons. And what happens is that in the near horizon region, we can think about the propagation in the near horizon region as depending on the scaling dimension of the mode. While in the faraway region, we could think about how the mode is suppressed because of the potential barrier, where the potential barrier roughly comes from the angular momentum of the mode. Now, for gravitons, angular momentum is higher, so the potential barrier is higher than for photons. But it turns out that because of the change in the wave equation due to the graviton-photon mixing, the scaling dimension in the near horizon region of the relevant mode of the graviton is actually smaller than the scaling dimension for the relative mode of the photon. This has a scaling dimension free in ADS. The photon has scaling dimension free in ADS2, and the graviton has scaling dimension 2. And the smaller the scaling dimension, the easier it is for the mode to propagate outside of ADS2. And it just so happens that the difference in scaling dimension, the fact that the graviton has slightly lower scaling dimension, exactly compensates for the fact that there is a higher potential barrier outside of the near horizon region that suppresses the gravitons. So this is at the end of the day what gives you roughly the same rate.
Okay. Thanks.
But the exact coefficient depends on multiple things. It depends on, well, yeah, it depends on the exact form of the wave equation. And it depends on the number of polarization modes that the photons and graviton has, which are also
Right.
different.
Yeah.
I think this factor of 4 might come from additional polarization modes, but I don't remember off the top of my head.
Right. Thanks.
Okay, there's some unfortunate news, which is that all the calculations that I've shown so far assume that the black hole is bosonic. And the result actually changes in quite a funny way if we assume that the black hole is fermionic. By fermionic, I just mean that it has half-integer angular momentum. Um, so for fermionic black holes, the selection rules are actually different. So previously, the thing that stopped us from emitting photons in the lowest state was the fact that 0 times 1, the spin 0 representation times the spin 1 representation, only contains the spin 1 representation and not the spin 0 itself. But if the black hole is fermionic, the selection rule tells us that if we emit a photon, we could actually remain in the spin half state of the black hole. So if a black hole that's fermionic cools down, it will eventually end up with in the spin half state, at which point it will actually still be able to emit single photons because a photon can still keep it in the spin half state. And this enhances the evaporation rate. So actually, fermionic black holes go a lot quicker towards their extremality bound than bosonic black holes until they emit a fermionic particle. But the fermionic particles that they would emit in our own universe would be the charged ones. So this is why the next thing that we should do is study the evaporation rate into charged particles. So we want to answer whether the evaporation rate is into charged particles is also affected by quantum gravity effects at very low temperature. And naively, thermodynamics would say that it is. Namely, you could estimate, people have done calculations in the past that estimated the decay rate into charged particles by taking the difference between the entropy of the black hole before emission and the entropy of the black hole after emission. Now, the entropy of the black hole before emission is given by some initial mass and some initial charge. And after emission, it's given by a new charge and new mass, where we just determine the new mass just from energy conservation. So we take the old mass and subtract the mass of the electron. And in principle, we should also subtract any kinetic term that the electron has when it gets to asymptotic infinity. But at least naively, it seems that if we start out with a black hole that had an entropy, sorry, that had a mass that was arbitrarily close to the extremal bound, so it was very close to extremal, we would end up with a black hole that's far from extremal afterwards. So as we've seen at the beginning of the talk, S before would get very large quantum corrections that are logarithmic in the temperature. And S after, whose logarithmic corrections depend on the logarithm of the temperature after the emission, would actually have only very small quantum corrections. So naively, this rate just gets very modified because the difference in entropies also seems to get very strongly modified. However, we have to do the calculation more carefully. Thermodynamic guesses oftentimes fail, and I'll actually explain why this argument fails in a few minutes. So to compute the evaporation rate into charged particles, we first want to understand the back reaction that a charged particle has on the space-time in order to see how the metric fluctuations affect the dynamics of this charged particle. So the Schwinger pair product, normally the Schwinger pair production rate can be computed by going to Euclidean signature and finding instant configurations, so world line configurations of the charged particle to compute the new partition function of the black hole in the presence of the instanton. Now, the instanton that's relevant here is the world line of a particle moving in an electric field in ADS2, and such world lines were actually studied a long time ago by COMTET. And such world lines are simply given by circles in the near horizon region. However, there is a problem with this computation, which is that the particle, right, this instanton, can be anywhere in the near horizon region since the space is homogeneous. There's no preferred location. So there's actually there's two translational modes, the ones that go to the left and to the right and up and down in ADS2, in Euclidean ADS2, that we have to worry about and integrate over in order to get the partition function in the presence of the instantons. And you might wonder whether these translational modes get lifted, just like the Schwarzian modes that we saw at zero temperature got lifted by quantum effects. And these translational modes are generated by two of the free generators of the SL2R isometry. Namely, if you act with an SL2R transformation on the metric, the metric of the spacetime won't change because it's an isometry, but it will change where the boundary is relative to the location of the instanton. So that's effectively what can move the instanton in the near horizon region. And these two SL2R modes are actually what we encountered they correspond to two of the modes in the Schwarzian action that have zero weight. So that's how we see that if we neglect the back reaction of the world line on the space-time, we actually see that there's these two exact zero modes. But it turns out that including the back reaction of the particle in the space-time actually gives weight to these modes and affects the Schwarzian perturbation theory, making the instanton calculation under control. So therefore, we have to calculate what the new instanton is when we include the particle in the space-time. And this can be done by coupling the action of this instanton to the action of Einstein-Maxwell. And the resulting back-reacted solution can be computed exactly. It's given by two black hole solutions that are glued together at the location where this instanton lives. One has mass m and q, and the other one has mass m bar and q bar. Now, the solution for the black hole inside of the instanton turns out to exactly give you the ADM mass and charge of the black hole after emission. So we can compute we can solve the equations of motion and compute this instanton exactly. And what we find is that, first of all, the area of the instanton is very small in ADS units. This means that, as I said earlier, to a good approximation, the instanton lives in flat space. Second of all, the presence of the instanton makes the temperature inside and outside of the instanton region slightly different. And this difference in temperature effectively leads to a small defect being present if we continue the space-time from outside of the instanton past where the instanton is located. Now, the angle of this defect, the opening angle of this defect, we can characterize it by 2 pi times alpha. So alpha equals 1 means that there's no back reaction and no defect. Alpha slightly different 1 means that the back reaction is small. And this is what we find. We find that essentially putting in the instanton causes this effective defect to appear that has an opening angle that's very, very close to 2 pi. The third thing that we notice is that the new mass that the black hole has inside of the instanton, so this is also the mass after emission, is actually very different than what you would naively expect, which is that the black hole would just lose energy that's just given by the mass of the particle. Instead, the black hole remains much, much closer to extremality than you would naively think. But it still goes much above the breakdown scale. Translating this into what the properties that the electron has, the electron gets thrown out, or the positron has. The positron gets thrown out along this blue line at asymptotic infinity. And by the time it reaches the asymptotic infinity, because of the electric field that the black hole has, it actually becomes highly relativistic. So a positron, when it gets emitted, it gets accelerated and gets relativistic mass by the time it reaches asymptotic infinity. That's essentially very close to the Planck mass, up to factors of the fine structure constant, up to a multiplicative factor of the fine structure constant. Um, Finally, the action of the instanton in the presence of the black hole, so the action of the black hole, sorry, the action of the entire space-time, is actually given by the new entropy of the black hole after the instanton gets emitted. So this R bar plus is the new radius of the new horizon radius of the black hole after the instanton gets emitted, and we find that the instanton action plus black hole is exactly given by the entropy that we used in the thermodynamic argument previously. However, what's more interesting is what happens when we take into account quantum effects in the presence of these instantons. So what happens is that the Schwarzian modes, the n equal 1 and -1 modes that correspond to translations, get slightly lifted, and they get lifted precisely by the difference between 1 and this defect angle alpha. So this means that we can recompute the one-loop determinant of all the modes in the presence of the instanton, and instead of getting something that goes like temperature to the 3/2, we obtain something that goes like temperature to the 1/2, multiplied by the contribution that comes from the instanton itself. Okay. And from this, we can actually compute using the ratio between the partition function of the black hole plus 1 instanton divided by the partition function of the black hole. This should give us e to the I times the decay rate times beta, the pair production rate times beta. And in the regime in which we only use one instanton in the expansion, we can obtain what the decay rate is to leading order. And what we surprisingly find, even though we've accounted for all these quantum gravity effects, is that the decay rate remains completely unchanged. This value, beta E breakdown times e to the minus I instanton effective, actually gives you the same result that I showed in the beginning slide that Zwinger would have computed with a constant electric field in the near horizon region. So why did our thermodynamic guess fail so miserably? Well, as we've seen in the Euclidean picture, the instanton gets emitted. This is the black hole before emission, and this is the black hole right at the moment when the pair gets produced. Here is the red is the positron and the blue is the electron. And right at the point where it's produced, the geometry outside of the location where it's produced remains largely unchanged, right? It's only once the positron is accelerated by the electric field of the black hole that it escapes all the way out to infinity that the black hole actually changes its temperature. And the positron escaping from the throat all the way out to infinity is a thermodynamic irreversible process. So therefore, we shouldn't actually be comparing the entropy after emission to the entropy before emission. We should be comparing the entropy before emission to the entropy right when the instanton was created. And that's what essentially the calculation that I showed you previously does. And that's what leaves the Schwinger rate completely unchanged. And we can actually also do a resummation of instantons at the level of the gravitational path integral. This slightly changes the dilute gas approximation, but it turns out that if we resum the contribution of all the instantons, we get Schwinger's answer to leading order and subleading answers that break the dilute gas approximation at subleading order. One interesting thing is that when the instanton action becomes small, namely when the charge of the black hole approaches that 10 to the 44 coulombs, these instanton, the breaking of the failure of the dilute gas approximation actually becomes important, and these terms become comparable to Swinger's answer. So in the future, it would actually be interesting to see how these additional non-perturbative effects change the result. So this brings me to the final point, which is the evaporation history of a charged black hole. Could I have 3 more minutes if you don't mind?
Sure, sure. Yeah, yeah. Go ahead.
Okay, so we start with a black hole that has some mass m and charge q and angular momentum j. We lose all the angular momentum first. We end up in this plane. Afterwards, we radiate Hawking radiation. That's mostly neutral since charge radiation is highly suppressed. And this Hawking radiation is well described by the QFT curved space-time approximation up to the point where we hit this energy breakdown scale that's shown in by the dotted black line. At this point, quantum corrections kick in, and the black hole gets closer and closer to extremality. It gets exponentially close to extremality, at which point an electron is emitted. So here in the first epoch of evaporation, we can assume that the black hole is bosonic, for instance. Once an electron is emitted, it becomes fermionic. And after the electron is emitted, again, the semi-classical calculation will be valid for some time, at which point quantum corrections will kick in, but this time we will be able to emit single photons instead of diphotons, as we did in the first epoch. So this is the second epoch of a black hole. It's a fermionic epoch. Again, it will emit an electron, and it will go back to a bosonic epoch in which the semi-classical evaporation rate will be valid. Eventually, you will radiate into neutral particles. Sorry, eventually you'll start radiating diphotons, and you'll emit an electron again, and this tick-tock process will keep repeating and repeating. How long will it keep repeating? Well, it will keep repeating up to the point where the charge of the black hole will be comparable to 10 to the 4 coulombs, or the charge measured in Planck units will be comparable to 10 to the 6 solar masses. At this point, the black hole will deviate sufficiently from extremality for quantum effects to no longer be important. And instead, it will follow this curve that is obtained by using just the QFT curved space-time approximation. And then we can describe what happens to this black hole very accurately up to the point where the black hole becomes Planck mass. So all the way down to Planck masses, the temperature will be much larger than the breakdown scale, and the black hole will essentially be semi-classical. Okay, but however, I want to emphasize that because this evaporation process is so slow, most of the lifetime of a black hole is actually spent in these regions where quantum gravity corrections are crucial to describing the evaporation rate. Okay, so to summarize, charged black holes with large enough charge get incredibly close to extremality when left to evaporate in vacuum. Close to extremality, quantum corrections drastically affect the rate of Hawking radiation for neutral particles, but don't have as big of an effect for charged particles. And these corrections completely alter the history of a black hole, even for the simplest observable, such as a thermometer that's placed far away from a black hole. So I'll just leave some points of discussion here on the last slide, and I'd like to thank you and ask if there's any questions.
Thanks very much, Luca, for this excellent talk. Thanks a lot.